Hi everyone. Thank you for coming to my talk. I am doing my final year in my PhD studies, so I'm looking at innate immunity. But my talk today is how you can apply the principles of immunity to space exploration, and what I've been thinking about is how we might take these great ideas that the students have, and what's the first step? What's something we can build now? In thinking about who's going to go to space, I thought there might be three groups who have reasons why they're going to space. There's a small group of people, like everyone at this conference, who, although there's something interesting or useful to do, I haven't got a mouse pointer. Because it's there, they're a group of hardcore space enthusiasts who, if you offered them a trip to Mars, a one-way trip to Mars, they would take it. Doesn't matter if they come back, they would be happy to take it. Pretty much. Then you've got the most of us who are more practical, who they want to have something interesting or useful to do once they're in space. But then there's pretty much the rest of everyone who, it's just another location. If their friends and family are there, then they'll go to space. The reasons people will stay in space, first group will go for any reason. The third group will stay because their friends and family are there. But really, it's this second group of people that we have to attract. They have to be healthy, they have to have meaningful work. Thinking about the length of time it actually takes to get to our destinations in space, the Earth-Mars round trip, 18 months, might take a bit less if we have advanced propulsion technologies, but just about anywhere else is going to take longer than 18 months. And if you think about any location that you're willing to spend 18 months living your life in, pretty much for the vast majority of people, the spacecraft itself has to be somewhere you're willing to stay. Can we design spacecraft which are capable of sustaining numbers of humans away from Earth? Are they going to be like these torus-shaped spacecraft? What challenges do we need to address? Obviously, there's microgravity. We know that it causes deterioration in bone density and muscle mass, and we also know that there are immune system issues with being in zero gravity for an extended period of time. Now, there are drugs like denosumab, was published fairly recently, last year I think, which helps to address the way that bone deteriorates in space. So you have this drug that you can potentially give to astronauts when they come back, and they will have better recovery rates in restoring bone mass. But really, this is the first toroid space station that I've seen, like Arthur C. Clarke. Von Braun actually designed this back in 1952, and he understood that the best solution is something that is simple, that you don't need active energy to maintain it. Now, one thing that, like all the students pointed out, the diameter of the space station is important, because his diameter was only 76 meters, as opposed some of the student groups were a lot bigger. But the important thing is that if you have a 1% difference in acceleration between your head and your feet, you start to get vertigo, or if it's any higher than that. So you need to have a diameter for something of a human scale. You need to have it that's 76 meters, and I'm just pointing that out for later in my talk. There's a second challenge, air, water, waste, recycling. Currently on the International Space Station, oxygen is generated electrolytically from water, and the hydrogen gas that's produced as a byproduct of that is actually vented into space. CO2 is recycled by mechanical filtering systems, and you've got these charcoal filters that filter all the poisons and toxins out of the air. Now, this is not sustainable once you get away from Earth, where these systems are manufactured. These are they're not closed systems, they need parts that are manufactured on Earth. So there was this group, Shalef et al. In 1970, that proposed using algal reactors, and they calculated that 500 to 600 grams, so a pound of algae per person per day, was enough to recycle all the oxygen needs as well as filtering the air. Now, perhaps long-term solutions will involve this. Third challenge, food production. Now, what they're actually doing on the space station at the moment, they've got this LADA experimental bank. The ISS crew members have been growing radishes, wheat, lettuce. They're all very small scale, obviously, but the amount of effort it takes to grow vegetation in microgravity, they've got long release fertilizer, they've got special wicks that make sure the roots grow down and the leaves grow up, and it's all very specialized and takes a bit of work. So much of the complication with growing vegetation will be removed once we have a spin gravity environment, and eventually, like the students were saying, this will be scaled up to provide the majority of air, water and waste recycling. These are just ideas and experiments so far, and although I love the ideas of making these massive space station, I'm looking to see what we can do soon. So the problems with these, they're more complicated to implement, they're more costly to launch, and we haven't yet researched what kind of maintenance requirements we're going to need. So beyond low Earth orbit, I would say that there's actually not that much of a distinction between a space station and a spacecraft. Where you live when you're traveling 18 months to Mars or to Jupiter or wherever is going to have to be a toroid space where you're growing your food, you're recycling your waste, you're recycling your water. And I think there's a fourth challenge that I haven't heard addressed much in the media, and that is that aside from all of these other reasons you might want to have plants and other biomass in space, immunologically you need to be challenged by pathogens in order to stay healthy. The Hygiene hypothesis, which is published in 1989, is basically saying that if you don't play in the dirt as a child, then you're going to get sick as you grow up. You need to be exposed to various different antigens, and so what happened, if you're looking at this as a time scale, when you're a newborn baby, you've got your mother's antibodies, which transfer across the placenta into the newborn baby, and they last for about 6 months of the start of your life. They protect the baby. But after that, what you need is this antigenic challenge, the pathogens that are in the environment, and it's from that that you build up your immune system and your memory T cells, your various other immune cells that learn how to see pathogens in the bloodstream, see it in your lungs or mucous membranes, and actually respond to that. So if you don't get those antigenic challenges, you have impaired immune development. This is arguably important for adults as well. Regular antigenic challenge from a diverse variety of sources. You have interferon gamma, it's a cytokine. It's something that your white blood cells produce when they see bacterial, any kind of bug pathogen. And what we're finding now in the molecular studies of immunology is that you actually need this interferon gamma to be produced in order for your white blood cells to differentiate properly. So that is one reason that adults will possibly not stay healthy if they are not constantly challenged by dirt in the environment. And this is kind of a different story from what we're seeing so far in the ISS, and every spacecraft that's gone up. The astronauts have been subject to quarantine. There've been extensive health checks, and this is not going to be the future of the space going public. If you want to go up on the space shuttle, you don't want to have to wait in quarantine for a week before you go up. Once these things become routine, there are going to be sick people that get up into space, and if people do not have strong immune systems up on space stations or spacecraft, then that can be a problem. So the other point is that no one astronaut, I think the longest individual stay on a spacecraft has been around 6 months, and cumulatively some astronauts have stayed up for a couple of years, but this is not long enough to see the kinds of problems like type 1 diabetes, multiple sclerosis, some of the other diseases I mentioned, to see those in astronauts. So this might be a problem that we don't see until we start staying up for long periods of time. But if this is going to be a problem, then we need to make our design decisions now, and this is something that I think is worth investigating now. So what I've done, I've designed Carousel Space Station as an idea, a model spacecraft which will use a mouse model to answer this question. Is it important to have constant immunological stimulus? So mouse models are useful. We use them all the time in biotech industry. Various different strains of mice are well characterized. They also have short intergenerational cycles, so we can test whether the sterile environment is going to be a problem with mice, with mammalian immune systems. And they're also small, and like going back to what I said earlier, they can be put in a smaller torus without being affected by the rapid rotation rate necessary to generate one Earth gravity. So primary objectives of space station is to launch and deploy a scalable modular system which can generate centripetal acceleration equal to 1 g. Use that mouse model to test the effect of different environments on mice in space and do that over generations. We want to gather data on how multiple species will interact together in close quarters module of a spacecraft, and if possible find a modular environment which is completely self-sufficient and therefore self-perpetuating. That way that when you have a new spacecraft up there and you need to develop these systems, you don't have to send parts up from Earth, you just transfer some of the life across from the module. So